In this video tutorial, we will introduce the concept of chemical reactions involving simple hydrocarbons. In general, there are four broad categories of organic reactions. They are the addition reaction, elimination reaction, substitution reaction, and the oxidation-reduction reaction, also known as redox. That being said, some reactions do fall under more than one category. For instance, many reduction reactions also fall under the category of addition reactions. Now, as this is an introductory chemistry course, we won't be going into too much detail with regards to the reaction mechanisms, but instead we'll focus on pattern recognition so we can get a general overview of the many different types of organic reactions. So let's start off with addition reactions. Their pattern is very similar to those that you would have found in grade 10 and grade 11 chemistry when you were talking about synthesis reactions, where you started off with two smaller elements or compounds and combined them together to make a larger compound. Well, the same pattern can be seen with addition reactions. One of the signs that an addition reaction has occurred is the removal of a multiple bond. So over here we see the presence of a double bond in the reactants between the two carbons, but in the product that double bond has disappeared. So during an addition reaction, the double bond breaks, becoming a single bond, but that opens up two new sites because carbon must always have four bonds. 1, 2, 3, and the fourth bond is attaching to the carbon. Same thing on this side. But by turning this double bond into a single bond, I open up two new sites, allowing me to add the X to one of the carbons and the Y onto the second carbon, resulting in a larger compound being formed. Alright, so don't worry about how the double bond breaks or the specific details of this reaction mechanism. Instead, I want you to focus on the overall pattern for this reaction. So don't worry about how it's happening, but focus on what is happening. Alright, looking at example 1, we will again break that double bond, turning it into a single bond, which in turn opens up two new bond sites, where I can add on the hydrogen to one of the carbons, and a bromine to the other, forming a larger compound, in this case bromoethane. The same thing happens with the triple bond, except instead of turning into a single bond, it only becomes a double bond. Again, two new bond sites will open up, allowing me to latch on one of the bromines to one of the carbons, and the other bromine to the other carbon. This converts an alkyne into an alkene. Now, if I react this compound with another bromine molecule, I would be breaking the double bond into a single bond, opening up two new sites, allowing me to latch a bromine onto each of the carbons. And that is the pattern for addition reactions. Elimination reactions are the exact opposite of addition reactions. We start off with a large molecule that breaks apart into two smaller molecules. So it's very similar to the decomposition reactions you learned back in grade 10 and 11. So we start off with X and Y being removed or eliminated, if you will, allowing these empty bonds to collapse together, forming a double bond. So one of the signs that an elimination reaction has occurred is seeing a double or triple bond form when there had previously only been a single or a double bond. So alkanes turning into alkenes, or alkenes turning into alkynes. Looking at our first example, anytime I see an H and an OH side by side, I automatically think of water. So please start thinking of water as hydrogen hydroxide instead of H2O. It definitely makes things a lot easier for you to visualize the chemical reaction and the patterns involved with the reaction if you can see the H and the OH separately. So once again, we are eliminating the hydrogen and hydroxide, releasing water in the process, and allowing these empty bonds to collapse, resulting in the formation of a double bond. Now, you may notice that sulfuric acid is written above the arrow. This is because it is acting as a catalyst to speed up the reaction. So if you recall, catalysts do not participate in the overall net reaction. As such, they are neither written on the reactant side, nor are they written on the product side. Instead, they just sit above the arrow to show the reader that it helps the reaction proceed forward. In example 2, we see a single bond becoming a double bond, which is a sign that an elimination reaction has occurred. Again, the H and the Br are removed from the molecule to form hydrobromic acid, and now that they have been eliminated, the empty bonds can then collapse to form a double bond. So we're going from an alkane into an alkene. So if an addition reaction is like synthesis and an elimination reaction is like decomposition, then substitution is like a displacement reaction where they are going to switch partners. So in this situation, Y and X are switching places. Looking at example 1, as I said before, anytime I see an OH and an H that are side by side, I automatically think of water being produced. So in this case, the OH and the iodine are switching places, with the iodine latching onto the hydrocarbon while the hydroxyl latches onto H to form water. In example number 2, the bromine and the NH2 are going to switch places, allowing us to attach an amine group onto the hydrocarbon while allowing the bromine and the hydrogen to form hydrobromic acid. As I mentioned before, some reactions do fall into more than one category. As an example, condensation reactions are a special type of subcategory for substitution reactions. During a condensation reaction, two organic molecules combine together, in this case the carboxylic acid and the alcohol, to produce a single organic molecule, in this case an ester. Quite often a smaller molecule, in this case water, is produced. As I will keep mentioning throughout this video, anytime I see an H and an OH that are side by side, I automatically think of water, so the H and the OH pop out to produce the water. And with these two parts gone, the carbon can latch onto the oxygen, forming an ester bond. And this is one of the reasons why esters have a different naming system than other functional groups. So for instance, this ester is called 3-methylbutyl ethanoate. You'll notice there's a space inside of its name when no other functional group has that feature. This is to help the reader visualize how the ester was formed from the carboxylic acid half and the alcohol half. Again, we see sulfuric acid is written above the arrow to show that this reaction is acid catalyzed and requires an acidic medium to proceed. Now, with a condensation reaction, water pops out. But what if we were to add the water back in? Well, you would get hydrolysis, which is the reverse of a condensation reaction. Looking at the ester bond, we're going to add water back in. Again, I highly recommend that you think of water as hydrogen hydroxide to help you visualize the pattern, because we're going to add the OH to the carbon over here, allowing you to form your carboxylic acid, while placing the hydrogen over here on this oxygen, so you can form your alcohol group. This in turn splits the ester bond, releasing the carboxylic acid half and the alcohol half. Again, this reaction is acid catalyzed and is a subcategory of a substitution reaction. The last category that we'll be looking at is that of oxidation and reduction reactions. Because they occur simultaneously, while one reactant is being oxidized, the other one is being reduced, quite often we refer to them as redox reactions. For this unit, we will focus only on the organic reactant. Is it being oxidized or is it being reduced? Just be aware, if the organic molecule is being oxidized, then someone else must be reduced. And of course, if the organic molecule is being reduced, then someone else must be oxidized. We will be using a different definition for redox reactions when we get to the electrochemistry unit. But for now, if the carbon atom forms more bonds with oxygen or less bonds with hydrogen, then we say that the organic molecule has been oxidized. So in this situation, we only have one bond with O and one bond with H to this carbon. But after the oxidation process, we now have two bonds with oxygen and no bonds with H on this carbon. The same goes with this example. Two bonds with O, one bond with H. After oxidation, we now have three bonds with oxygen and no more H atoms are attached to this carbon. So these are all examples of the hydrocarbon making more bonds with oxygen and less bonds with hydrogen. With reduction reactions, we have the exact opposite, whereby the carbon atom will form less bonds with oxygen or more bonds with hydrogen. So in this example, the carbon has formed two bonds with oxygen, but after the reduction process, it now only forms one bond with oxygen, and it's gained a bond with a hydrogen. In this example, none of the carbons are bonded with oxygens or hydrogens, but after the reduction process, we now have formed more bonds with the hydrogen. So just remember that you don't have to make less bonds with oxygen and more bonds with hydrogen. As long as one of these situations has occurred, we say that the hydrocarbon has been reduced. All right, let's try out a couple of questions. Press pause, and when you're ready, press play, and we'll take up the answers. In example A, I see an OH group, and I see an H group, and then I see water. So that usually tells me that there's going to be a substitution reaction, specifically condensation, because water is being released. So what's happening over here is the bromine and the hydroxyl group are going to switch places. And so the bromine is located here now, while the H and OH have formed water. So reaction A is substitution. In example B, I see a double bond, and then the double bond is gone. So that tells me it's going to be an addition reaction, where the double bond breaks up, turning into a single bond, opening up two new sites. So each of these chlorines can latch on to either side of that double bond, forming a dichlorohydrocarbon. Finally, in the last example, we start off with an alkane, only single bonds present, but end up with an alkene, so there's a double bond there. This means that it must be an elimination reaction. Now, normally we don't explicitly show the hydrogens, but I'm going to put the hydrogens in so you can visualize how the elimination process works. We are going to eliminate the H and the Cl, so that hydrochloric acid is formed. And with these two gone, the empty bonds can collapse to form the double bond. In our next example, we see that we had 2 bonds with an oxygen attached to this carbon, but in the product we now have 3 bonds attached to the oxygen from the carbon. So that shows us this is an oxidation reaction, because we're making more bonds with O. Down here we only had 1 bond with an H on the 3rd carbon, but over here on the 3rd carbon we now have 2 bonds with H. So that indicates a reduction reaction, as we are making more bonds with H. And with the last example, we had the 2 bonds with O, but now only 1 bond with O. So this too is a reduction reaction, as you're making less bonds with oxygen. Alright, so try these questions out on your own, but I'm going to move on to the next section. In grades 10 and 11 chemistry, you would have been introduced to this chemical reaction, the combustion of hydrocarbons. So let's do a quick recap. During a combustion reaction, oxygen is always required. If you have excess oxygen, so more than you need, then we have a complete combustion reaction, in which case you'll produce carbon dioxide gas, water, and heat. But if you have limited oxygen, so not enough oxygen, you end up with incomplete combustion. You'll still produce the same products, carbon dioxide, water, and heat, but you'll also produce carbon monoxide and carbon soot, so ashes. Although many organic reactions are reversible, due to the exceedingly high activation energy required to go in the reverse direction, most combustion reactions are said to be irreversible. So once a hydrocarbon is burned, it cannot be converted back into its reactants, at least not through this reaction. Another reaction involving alkanes is called cracking. Through the use of high heat and pressure, hydrogens can be removed, creating an unsaturated product, such as alkenes or alkynes. Since we're going from a single bond to a double bond, this is a type of elimination reaction. Now, to help us keep track of all the different types of chemical reactions we'll be covering in this video, let's create a flowchart that summarizes everything we learn. Over here, we just talked about cracking, where we are converting alkanes into alkenes with the aid of heat and pressure. Of course, hydrogen gas is released, and this is a type of elimination reaction. We should also note that this reaction must occur under anaerobic conditions. Anaerobic means no oxygen present, because if you take an alkane and add heat with oxygen present, you'll end up with a combustion reaction, producing CO2, H2O, carbon monoxide, and carbon, instead of the alkene you were hoping to create. Now, don't freak out when you look at this flowchart. I know at first glance it looks very complicated, but a lot of these reactions are repetitive. Remember, there's only 4 broad categories that we're going to be looking at in this course: addition, elimination, substitution, and redox. So once you start recognizing the patterns, and you see that they repeat themselves, it's not as bad as you imagine it to be. Alright, let's move on to the next reaction. The halogenation of alkanes, resulting in the formation of alkyl halides. Please note that the carbon-carbon bonds in alkanes are fairly hard to break, making them quite stable, and so you will not encounter any questions in this course that will require you to break the CC bond of an alkane. However, carbon-hydrogen bonds are much easier to break, and that allows us to swap a halogen for a hydrogen through a substitution reaction. So one of the hydrogens and one of the bromines will swap places, allowing you to halogenate this alkane, turning it into an alkyl halide. In the process, a hydrogen halide is formed. In this case, it is hydrogen bromide. However, heat or UV light is required for this reaction to take place. If the halogens are in their diatomic form, they are too stable to react readily with the alkane. So we need heat or UV light to first break them up, making them monatomic and unstable. In this unstable state, they will readily swap places, allowing this substitution reaction to occur. Please note that this only applies to bromine, chlorine, and iodine, as fluorine is already quite reactive and does not require the heat or UV light to start the reaction up. If I wish to add another halogen to this alkyl halide, I would just take this product and repeat the reaction again. Alright, so let's summarize what we just learned on our flowchart. We are turning an alkane into an alkyl halide. Here I have written that it is a substitution reaction for which we are substituting a halogen, which I will write as X2, where X represents whatever halogen we're trying to latch on, be it fluorine, bromine, chlorine, or iodine. This process is also called halogenation, and a hydrogen halide is produced. So HX, where again X represents whatever halogen you added on. In this case, it was a hydrogen bromide. But if you were reacting with chlorine, it would have been HCl. I have also included the reaction conditions, heat and UV light, though I might want to add in that fluorine gas does not require these conditions. Now, what happens if multiple substitution sites are available? Where would the halogen attach itself? So if I react propane with bromine gas, which of these hydrogens will switch places with the bromine? For this, we need to understand the difference between primary carbons, secondary carbons, and tertiary carbons. With a primary carbon, it is linked to just one other carbon atom, while a secondary carbon is bonded to two other carbon atoms. And I think you guessed it, a tertiary carbon is bonded to three other carbon atoms. This is important to know because primary carbons are the most stable, while tertiary carbons are the least stable. So primary carbons are unlikely to react, while tertiary carbons are more likely to react. In the case of propane, this would be a secondary carbon because it is connected to two other carbon atoms, while the carbons on either side are primary carbons. Because the primary carbons are quite stable, it would be difficult for the bromines to break the CH bonds at these locations, and it's more likely to react at this site, the secondary carbon, instead, because it's less stable and more likely to break. So this hydrogen will be substituted with this bromine to produce 2-bromopropane and the hydrogen halide, in this case hydrobromic acid. It is important to note that although the primary carbon is quite stable, making it unlikely to react, that doesn't mean it can't react. So it is possible for this hydrogen to be substituted as well, and that would produce 1-bromopropane. So with organic chemistry, anything that can happen does happen, and both these products will form. However, because 2-bromopropane is more likely to form, we refer to it as the major product, the one that will form the most. Meanwhile, 1-bromopropane is considered to be the minor product, as it is less likely to form. So on a test, you are expected to draw out all possible products and be able to label them as being the major product or the minor product, depending on how likely they are to form. And so one of the most annoying things about organic reactions is the production of unwanted byproducts. Making the products is the easy part. Purifying them is what takes most of your effort. So let's add this information onto our flowchart and remind ourselves that primary carbons are less likely to react, so they will produce the minor product, while tertiary carbons are more likely to react, resulting in the formation of major products. And secondary carbons are somewhere in between. Moving ahead, let's take a look at reactions involving alkenes, specifically the formation of alkenes from alkyl halides. Looking at the reactants, we see it's all single bonds. But on the product side, we've got a double bond having formed. And that is one of the signs of an elimination reaction. For this to occur, a strong base is used. Typically, it's going to be sodium hydroxide. And as you're aware by now, anytime I see a hydrogen and a hydroxide, I automatically think of water. So the hydroxide will steal the H, forming HOH, while the sodium will remove the bromine to form a metal halide, in this case sodium bromide. Once these two have been eliminated, the bonds can collapse, resulting in the formation of a double bond. So let's summarize this reaction in our flowchart. We are going from an alkyl halide to an alkene, and this is an elimination reaction. By removing a hydrogen and a halogen, so the HX, so the hydrogen and the halogen, we're going to remove them. In the presence of a strong base, so that was sodium hydroxide in this case, we end up producing water and the salt, also known as the metal halide. So there's the water and the metal halide salt. And of course, the alkene is produced. Alkenes and alkynes can also undergo addition reactions, as multiple bonds are less stable than single bonds. As such, alkenes and alkynes are generally more reactive than the alkanes, which is why the halogenation of alkanes required heat or UV light to start the reaction up, but due to the high reactivity of multiple bonds, just room temperature is enough energy to activate the reaction. Heat and UV light is no longer required. Looking at this reaction, we see a double bond turning into a single bond, which is one of the signs of an addition reaction. So we're going to break the double bond, resulting in the formation of a single bond and two new sites being opened up, allowing the two bromines to latch on to each side of that double bond. And this produces a dibromoethane. Now, be careful. When you're halogenating a multiple bond, both halogens get added on. So you end up with two halogens in your alkyl halide. However, the halogenation of an alkane is a substitution reaction, so only one bromine gets latched on at a time. If I wanted two bromines, I would have to repeat the reaction again. So trying to produce dibromoethane from alkane requires you to do the substitution reaction twice, but producing dibromoethane from an alkene only requires you to do the addition reaction once. Alright, let's put this into our flowchart. We are going from an alkene to an alkyl halide. It is an addition reaction, X2 being the halogen. Only room temperature is required, so no heat or UV light. And this reaction is called halogenation. But what if I only wanted one halogen on my product and not two? In that case, we can use hydrohalogenation. So adding a hydrogen halide, HX, instead of the diatomic halogen. So again, we will break the double bond, opening up two new sites. So hydrogen can latch onto one of them, while bromine is added onto the other. And now only one halogen is added on instead of two. Again, because a double bond is involved, there's no need for heat or UV light to start this reaction up. Just room temperature is enough energy to get this reaction going. But now we have another problem. By breaking the double bond and opening up two new sites, how do you know where the hydrogen will be added? In such cases, we will follow Markovnikov's rule, which is basically summarized as the rich get richer. So what that means is whoever has more hydrogen should get the hydrogen. Since carbon number 1 is attached to two hydrogens, while carbon number 2 is only attached to one hydrogen, carbon number 1 is considered to be richer and is more likely to have the hydrogen added onto it, making it more saturated with hydrogens or more rich with hydrogens. And once you know where the hydrogen goes, the bromine is going to be placed on the other remaining carbon. But as we saw before, just because something is unlikely to occur doesn't mean it's impossible to occur. And anything that can happen does happen. So according to Markovnikov's rule, the hydrogen is most likely to attach to this site, making 2-bromopropane the major product. If, on the other hand, the bromine latched onto the number 1 carbon instead, you would form 1-bromopropane, which would be your minor product. All right, so let's put this on our flowchart. Again, it's an addition reaction with an alkene, but instead of adding on a halogen, we're adding on a hydrogen halide. But we'll want to remember to follow Markovnikov's rule to determine which side gets the H and which side gets the halogen. In addition to reacting with halogens and hydrogen halides, alkenes and alkynes can also undergo addition reactions with water in a process known as hydration. I hope you're starting to see the pattern here, but the double bond is going to break, forming a single bond and opening up two new sites. Remember to always think of water as hydrogen hydroxide, so that one of the H's can be added on to this carbon, while the other OH will be added on to this carbon. This reaction is acid catalyzed, so we'll write H2SO4 above the arrow, and now you've created 2-propanol, or propan-2-ol, which is how I prefer to write it. Again, we will follow Markovnikov's rule, because this hydrogen can be added onto this carbon or this carbon, producing propan-2-ol and propan-1-ol. Since the rich get richer, and this carbon has two H's, while this carbon only has one H, that means the hydrogen is more likely to latch onto this carbon, carbon number 1 instead. Meanwhile, the OH is more likely to be added onto carbon number 2. Making propan-2-ol the major product and propan-1-ol the minor product. Let's go ahead and put this all on our flowchart, going from alkenes to alcohols through an addition reaction involving water and sulfuric acid catalyst. This, of course, is a hydration reaction. And let's remind ourselves that this reaction also follows Markovnikov's rule. The last addition reaction involving alkenes and alkynes that we're going to look at is called hydrogenation. Please do not mix it up with hydration. With hydration, you're adding water, while hydrogenation, you're adding in hydrogen. You guessed it, we're going to break this triple bond and turn it into a double. This opens up two new sites, allowing us to add both hydrogens to either side of that double bond. And if we repeat this reaction again, we break the double bond and turn it into a single bond, opening up two more new sites so that a second hydrogen molecule can then latch on to either side over here, and we're back to having an alkane. The required conditions for this reaction are heat and pressure, and typically a metal catalyst is used, such as palladium, platinum, or nickel. All right, let's put this one on our flowchart. And we're going from an alkene into an alkane. So again, this is an addition reaction, and we're adding in hydrogen gas, nickel catalyst, or heat or pressure, and this process is called hydrogenation. So that wasn't too bad. Congratulations, we have now covered this part of the flowchart. In our next video, we will look at the remaining organic reactions you are responsible for.